Okay, we have started with our format as last time. So we started with chapter 11 and we discussed about how solids and liquids are different from the gases. And we also discussed how we use the kinetic molecular theory to describe liquid and solid in addition to how KMT was really used to describe the behavior of the gases. And also during the last meeting, we also described what is so-called vapor pressure, wherein we mentioned that vapor pressure is just some sort of a property that looks at how easy it is for a liquid material to become solid. Okay, and we said that usually those that have lower intermolecular forces of attraction, they tend to uh, go to the gas phase in a much easier fashion compared to the one that has the stronger IMFA. Now, if I'm not mistaken, okay, we also have discussed about the Closius-Clapeyron equation, how we look at the relationship between pressure and temperature. So by looking at pressure and temperature, so any temperature changes would result to an increase in the vapor pressure. And the last topic that we have is about the phase diagram, wherein we look at the different temperature and pressure and how the physical states of a given material behaves, or what physical states do they have. So as I've told you, in the phase diagram, you will see the three phases of a given chemical. So you have here a solid phase, okay, a liquid phase, and the gas phase. So the boundary between the solid and the liquid, this is the conditions wherein both the solids and the liquid phase coexist. Okay, so the one between the solid and the gas, that's where the solid and the gas phase are in equilibrium. And the one between the liquid and the gas, like this one, this is the condition wherein they are in equilibrium. Now, this is the phase diagram of the water. So as you could see here, at room temperature, okay, you can see that the solid and the liquid can exist. Okay, so if you want to look at the room temperature, is around this area here. So it's very liquid for the water at what we call atmospheric pressure. But if you're going to lower the temperature, it will become solid at at 0 degrees Celsius. And if you're going to increase the temperature, it will become gas. And you also have this point that we could call the triple point, because that's where the three physical state exists. Now, there's another point that we have here, okay, and we call it the critical point. Now, the critical point, this is the temperature and pressure wherein you cannot distinguish whether it is a liquid or a gas. Okay, so usually, how do you make your gas into liquid? One way to do that is by lowering the temperature. Another way of doing that is, if you're going to look at this gas, will become liquid by increasing pressure. Because if you increase the pressure, what will happen? The molecules will become close to one another. And if they become close to one another, there's a chance that there will be an intermolecular forces of attraction that can form. Unfortunately, in the critical point here, this is the temperature and the pressure that whatever you do, okay, you cannot distinguish whether you have there a liquid or a gas. So what you have there is a so-called supercritical fluid. And I'm going to discuss that today. Now, compare it with the carbon dioxide. So if you're going to look at the critical point here is what? 31 degrees Celsius and 73 atmosphere. So what can you say about this temperature? This is just room temperature. If you go to a warm country, compare it to the one with water that you have here. And another way for you to look at this is, how come this one has an increasing, or we could say a positive slope, how come this one would have a negative slope? So that tells you something about the water properties as we go on. And another way that we can look at is how carbon dioxide is different from water is look at this. So at atmospheric pressure, your carbon dioxide can only be either a solid or a gas. There's no way that it can exist in the liquid thing. That's why you call it dry ice. Okay. Now, in addition to pure substance to exist in three physical states, some materials, like the example that we have here, sulfur, exists in more than one solid form. Okay, so sulfur has two solid form, which is the rhombic form and the monoclinic form. Now you might ask yourself, what does it mean? Later on when we go on crystals, you will see what a rhombic and what a monoclinic form looks like. Okay, both of them are solid. So in this case, you're going to have what we call three triple states, but only one of them is the true triple state. So when we say true triple states, that's just the one that's made up of solid, liquid, and gas. And among this one, this is the true triple state. Okay, so we're going to go on the so-called critical point. So as I've told you, the critical point, it gives you the temperature at which the liquid state can no longer exist and the pressure at that temperature, which is your critical pressure. So above this temperature and pressure, there's only one state, and this is what we call a supercritical fluid. So if you go 30 degrees or 31 degrees Celsius for carbon dioxide and an atmosphere or a pressure that is equals to, if I'm not mistaken, 73 atmosphere, you can have this supercritical fluid. Now the question is, what are the applications for this supercritical fluid? Okay. So some of the applications of the supercritical fluid is in this one, in our neighborhood. What shop is this? Anyone? What do you think is the shop here?
Is that like a laundromat?
Laundromat? Specifically, what does it do?
Oh, they're dry cleaners.
Okay, so you have here this term dry cleaning. So why do you call it dry cleaning? What's the most sensible way of saying why is it not dry clean? Why do you call it dry cleaning? Anyone?
Because they clean your clothes and then they dry it.
Hmm?
And then because they clean your clothes and then they dry it. I don't know.
What else? How do you usually do the cleaning in all materials? It usually involves what?
Water.
Water.
Washing?
Yep. So do you think it makes sense they call it dry cleaning because they don't use water? Just like you call dry ice for carbon dioxide because it doesn't have the liquid phase at atmospheric pressure. So the same thing here. You don't use water here. Is that new to you?
Yeah, I didn't know that.
Is it the first time that you hear that dry cleaning don't involve water?
Yes, for me, yes.
I thought they wash the clothes.
Dry cleaning don't involve water. It involves a material called PERC. Perchloroethylene. Okay? So what does it do? It's going to dissolve the dirt right away. And they use this supercritical fluid form. So what can you observe if you go to a dry cleaner? Usually there what? A lot of smoke. Okay, but that's just what we call the supercritical fluid that comes out of it. Okay, it's not like washing with water. Nope. In water, you use soap. Here, what happened is those perchloroethylene, that's the one that will dissolve the dirt that you have in your clothes. So usually it's not a liquid. No, that's another way of using the starch. Okay, that still involve water. But dry cleaning, they use this material. And the same thing when you have with this one. What's the difference between these two? What's the difference of this compared to this one?
One is decaf and one.
Okay, so one is decaf. So what does a decaf means?
It doesn't have caffeine.
It doesn't have a caffeine. So caffeine is what? It's an organic molecule. So how are you going to remove your caffeine if you want to have a decaf? So traditional means you use what? Organic compounds, organic solvent known as chloroform, and then they just let it dry. So imagine you're going to drink a material that was exposed to an organic chemical. So what they do, they use a supercritical fluid like CO2, and what happens? So you have there your coffee granules, and then the CO2 would go there, applying 31 degrees Celsius and 73 atmosphere. So what it do, it's going to dissolve or extract or remove all the caffeine that it has. So that's what a supercritical fluids do. Okay, and it's around us. So instead using this organic solvent, you just use this supercritical fluid, which is CO2. And CO2 is what? So cheap. We have a lot of it. In fact, that's the reason why our planet is heating up. There's too much of CO2. Where does CO2 came from? Anyone?
The burning of fossil fuels.
Is it the burning of fossil fuel? What else? What's the source of this, what we call the CO2? I can see 52 reasons where they came from.
Ozone?
Huh?
Ozone?
Okay. Ozone? Where else?
Respiration.
Humans.
Okay. Right now, there are 52 persons that expel CO2 to the body. And who are those 52 persons? Those are the ones who are in Zoom meeting right now. There are 52 participants, and all of us are expelling CO2. Okay, we expel CO2. The plants need the CO2, and what does the plants expel? Okay,
Oxygen.
oxygen that we need. There's so much CO2 right now. That's why what we call cause of this climate change is the accumulation of CO2. Okay, now we go to some properties. So we're going to focus on the liquid properties. Okay, so we're just going to discuss here surface tension and viscosity. So surface tension, this is the energy that is required to increase the surface area of a liquid by a unit amount. And the values are usually given in joules per meter square. So when you say joules, what is the, joules is the unit of what? Anyone?
Energy.
Joules is a unit of energy. So if you're going to look at this surface tension, okay, so if you're going to look how surface tension happens, so maybe this illustration will show you how. So we have here some molecules. So if it's on this area, the molecules would interact with all directions or in all directions. But if you have the molecules on the surface, what happens? It will interact only with the molecules below it. So the one above it is the surface. What happened? The accumulations of these interactions will results to some sort of a net energy, okay, that if the surface area is enough, it can prevent that material from sinking. Okay, so surface tension arises because the molecules at the surface of a liquid experience a net force towards the center of the liquid. Okay, so surface tension is the reason why you observe this. Now imagine if you're going to place this needle in this position, what do you think will happen? If you're going to have the needle, so let's say like now it's positioned like this one. So there's enough surface, okay, for it to float. So the surface tension is enough, okay, for it to float. But if you place it like this, what happened?
It's
Okay?
gonna sink.
It will sink because the surface area is not enough. So the tension that you have there in the surface is not enough. But if it's what we call enough, most likely it's going to what we call float. And the same thing that you observe it, sometimes if you put, let's say, a droplet of water in a wax paper, you will see that it is forming like droplets, okay? Or if you observe it in some leaves, I don't know if you're fond of what we call observing something. I'm trying to see if I can show you some example here. So you will have an idea what I'm talking about. So let's say this one. So do you see this leaf with water? So what allow this what we call water to form droplets? Okay, it has a strong IMFA that hold the molecule together. So that's another example of this what we call the surface tension. Okay, so if you're going to look at this, try to imagine, let's say, a kerosene. And what you're going to do is try to put a drop of kerosene in the wax paper. So most likely what will happen, the liquid that you will observe there will be spread out because the kerosene doesn't have enough IMFA or strong IMFA to hold them together, unlike the water, which you're going to know later on. Okay, so surface tension is also the reason why if you use a capillary, so a capillary, that's a glass tube which has one end open and the other end closed. So if you put water on it, okay, most likely the water will rise. But if you're going to put mercury, like in this case, okay, what will happen? It will not rise. It will go down here. So it has something to do with the interactions that they have there. And again, surface tension is the one that dictates this property. Okay, so insects, they can walk in water because the surface that they have is enough for the surface tension to hold them. Who else can walk in water? Anyone?
Jesus.
Okay, so if you read the Bible, okay, there's a guy, acronym as JC. You can walk in water, Connor. Okay, and that was reported to walk on water. Okay, now another thing, another property that we have in terms of the liquid is the so-called viscosity. So this is the resistance to flow exhibited by liquid and gases. And this is best exemplified if you take your breakfast, if you use eating pancake, okay, and you add syrup on that pancake. So you will see, okay, if you're going to place glycerol and water, and you're going to let this metal bearing fall at the same time. So the flow of those, the one in the glycerol, is slower compared to the one with water because of its what we call viscosity. So one that flows slowly, we could say it's viscous material. Okay? An example of the viscous materials are the syrup that we have. So what can we say about the syrup?
It's viscous.
Okay? Usually the syrup are what?
What about toothpaste?
They're sweet, right? Because they're made up of sugar. So just like the surface tension, the viscosity is also affected by the nature of molecules that it has. Okay? So those that tend to have what we call a certain kind of IMFA, they tend to what we call become more viscous. How are you going to decrease viscosity? What do you think you can decrease viscosity? Anyone?
Add water.
Add water? No, the more practical way that you have discussed already in this chapter. You increase the
Temperature.
by increasing the T, you're going to decrease the viscosity. What is the T here?
Temperature.
Temperature. Just like what you do in hot molasses. Okay, so when you're going to increase the temperature by heating it, okay, what happened to the molasses? They become easy to flow. Am I right? Now, if we're going to look at the properties that we have discussed so far, so we have vapor pressure from the previous one, surface tension and viscosity right now. And this is where the molecular weight is. So what can we say? Can we observe some sort of a trend? So let's say if we increase the molecular weight, what happened to the vapor pressure? So the only one that is written here is maybe this one is lower, this one is low. But if you increase the molar mass, what happened? The vapor pressure
Increases.
What happened to the vapor pressure? So to the 4, to the 2, to the 2, to the 1, to the 0.
Will decrease.
It decrease, right? How about surface tension? So the only one that is always an anomaly is this and this one maybe. Right? So this is what? -3, -2, -2, -2, -2. Right? And if we're going to look at the viscosity, what happened? Again, what is the anomaly? The anomaly is this one and this one. If you're going to remove that, -5, -4, -4, -3, as the molar mass increases, it decreases the vapor pressure and increases the surface tension and viscosity. The only exception is water and glycerol. And today, we're going to determine why we observe that property. Okay? Or why this one is always an anomaly. So the pattern that we have, or the trend that we have, as you increase the molecular weight, the vapor pressure drops, but the surface tension and the viscosity increases. The only anomaly is the water and the glycerol, and we're going to discuss about that. Why? So it has something to do with the so-called intermolecular forces of attraction. Now, this is new to you. In your Gen Chem 1, what you discussed there is the intramolecular. So what's the other word for the intramolecular forces? Anyone? Those who are with me? Four-letter word. Pop culture. Anyone? What are those intermolecular forces that we have discussed from Gen Chem 1? Anyone? Four-letter word. A very popular pop culture. The bonds that we have discussed. Okay, what's the bonds that you discussed in Gen Chem 1? Anyone?
Ionic bonding.
So you have the ionic bond.
Covalent bonds.
Covalent.
Covalent.
Hydrogen.
Okay, so those are intramolecular because those are forces within molecules. Now, the one that we're going to discuss today is intermolecular. So this is between molecules. Okay, so this is what we call forces that hold the solids and the liquids together. If you want to make your liquid into a gas, then you need to apply some energy to break these forces. And the heat of vaporization, that's the energy needed to make a liquid into a gas. So if you're going to look at the neon, it liquefies at negative 246 degrees Celsius at 1 atmosphere. And the heat of vaporization for liquid neon is 1.77 kilojoules per mole. Now, where do we use this 1.77 kilojoules per mole? Okay, so you use it. 0.23 of that is used, okay, to push back the atmosphere when the vapor forms, and 1.54 kilojoules of that is used to break the IMFA. Now, the question, which do you think is stronger? The intermolecular attraction or the intramolecular attraction? So if you're going to compare the two, okay, this is the intermolecular, and if you're going to look at the approximate energy they have, this is what you have. Now for the chemical bonding, what do you have? It's a little bit higher. So how can you answer the question, which is stronger? The intermolecular forces or the intramolecular forces? Anyone?
The
Intramolecular.
chemical. Oh.
Okay. So the intramolecular is the stronger one. Remember, in the intermolecular, you're just breaking, okay, the solid into liquid, or you're just converting the liquid into the gas. But if you're going to break the intramolecular forces of attraction, what do? You're breaking the molecules into atoms. So let's say for the water, so if it's just IMFA, what you do here is water in the liquid form going to water in the gas form. If it's the bonding, what do? That's water, okay, breaking to form 2 hydrogen and 1 oxygen. So that's the difference. So the amount of energy to break the bonding is much higher compared to convert a liquid into a gas. Did everybody get that? So what we're going to discuss today is what are these intermolecular forces of attraction? So we have three here: the dipole-dipole forces, the London forces, and the hydrogen bonding. So if I'm going to do it, usually I do it like this, and this one like this, and this one's like this. So we're going to discuss these intermolecular forces. And the end game here is you should be able to identify what are the IMFA present in a given material. Okay? So totally, they coined the term van der Waals forces for both that has the dipole-dipole and the London forces. So what the van der Waals forces do is most of the all polar molecules, they exhibit dipole-dipole forces that results in the alignment of the molecules. So this is the solid and this is the liquid. So what's the main difference between the two?
Solid has a definite, like it's a definite shape, but liquid, all the shapes are different.
Okay, so the liquid shape is a little bit different compared to this one. So these are in a regular pattern. This one is a little bit what? Some of them is a little bit distant. That makes sense because this is a liquid and this is a solid. Okay, now what happened? So dipole-dipole, it exists if you have polar molecules. What is polar molecules? Anyone? What is polar molecules? When do we consider a material a polar molecules? Anyone from my class last time?
Polar molecules are basically molecules that have a big difference in the electronegativity.
Okay, there's a difference in electronegativity. So maybe that is true if you're just dealing with what? Two atom?
The shape is asymmetrical, so it would be polar.
FF and HF. So one has what? Equal sharing of electrons, while this one is an equal sharing, right? So between chlorine and hydrogen, where is the electron being abstracted to? Between hydrogen and chlorine, where is the hydrogen going to?
Chlorine.
Usually to the more electronegative. So we have this thing, and we have a partially positive end and a partially negative end, right? Now, how about if you have more than two atoms in a given molecule? What's the basis of the polarity? Let's say, how come H2O is polar while CO2 is not?
Brandon said it before, but he said it also depends on the symmetry.
The what?
The symmetry between.
The symmetry, but I'm looking for a term that we have in Gen Chem 1. So I will roll call now all the A student. What usually a polar molecule has? The term is there, repeated several times. So if you have, huh? What's that?
Is it dipole?
Okay, the dipole. Okay, you have a partially negative end and a partially positive end. So that means you have a dipole. But what usually is the basis for us to determine that the molecule is polar or non-polar? That's two words, and the first word you mentioned already. What's the term?
Is it the polarity?
No.
The electronegativity.
No.
Is it the direction of the electron?
I don't know if you remember this. Are you still familiar with the dipole moment?
Is it having partial positive and partial negative charges? No.
Yeah, but this one can have a partial negative and a partial positive. Here, look. That goes there, that goes there, because this is what, negative, negative, this is negative, and this is positive. But what does the dipole moment tells us?
The
The
shape?
difference in electronegativity is if you only have two atoms. That's there. What's the dipole moment?
The sum of forces.
Okay, the dipole moment is the sum of forces. So if you're going to look at the sum of the forces here, what is your dipole moment equal to?
The
Compared to water that has
0.
this. Anyone?
Isn't it the difference between electronegativity?
No. You cannot say it's a difference of electronegativity is in just two atoms. Do you have two atoms in CO2? Do you have two atoms here? Okay. So if you're going to look at the dipole moment, that is just the net charge. Okay. It looks at the net charge of all the direction of the electrons. So here, what is the dipole moment? That's equals to 0 because it cancels out. But here, the dipole moment is non-zero because the direction of the electrons is going towards the oxygen. You still remember that?
Sort of.
Well, we'll see, because the only way for you to determine what is the IMFA present is if the molecule is polar or non-polar. Okay? So when you have a polar molecule, you will have there the dipole-dipole forces. Now, there's no dipole-dipole force in non-polar molecules. But there is still what we call the force of attraction. Okay? And Fritz London explained this relationship, and he now call it London forces. In other, what we call book, they call it dispersion forces. For simplicity, combining the two, we will call it LDF, which is London dispersion forces. Okay? So in non-polar molecules, there's no dipole-dipole, yet there's still force of attraction. So we go to this, what we call LDF. So if you're going to look at this LDF that we have here, so in a non-polar molecule, usually, if you're going to look at the polar molecules, the dipole, non-polar molecules, the dipole moment is 0. If you have two atoms, there's an equal sharing, okay, of the electrons. But what is the nature of the electron? What can you say about the electron? It's negative charge, but what else? If you're going to look at the atom, the electrons are the one going around the nucleus. So it's always what? In motion. Now, there are some chances that in its movement, the symmetry that it has is compromised. So what happened? Okay, in any instant, the charge will become unevenly distributed. And in that case, there would be an instantaneous dipole. So if you're going to look here, so in some instances for neon, some of the electrons will go here compared to this one. So instead of a 5 to 5 where there's equal sharing, so what will happen? 7 of the electrons goes here and 3 left here. So there's more electrons here. So this will become partially negative charge. What happens if you have a neighbor? So the neighboring thing, the neighboring neon atom will also be instantaneously charged. Just try to look at it in terms of a domino, right? You place a domino side by side, and once one of the domino will fall, the other domino around it will also fall. So this is what the London dispersion forces happen, how LDF happen. So in the next moment, what will happen? The electrons move and the instantaneous dipoles change. However, the instantaneous dipole tend to change together, maintaining the attractive forces between them. So what is the effect of this? The bigger the molecule, the stronger is the LDF. Now, LDF is not only present in nonpolar molecules. It is also present in polar molecules. Okay? The only difference is the polar molecules also have the dipole-dipole. And if you have a dipole-dipole, it becomes more dominant than the LDF. LDF is the only one that is present in nonpolar molecules. Okay? So if you're going to look at this LDF, there are usually weak attractive forces between molecules resulting from the small spontaneous dipole that occur because of the varying positions of the electrons during their motion about the nuclei. And as I say, all molecules, including the polar, exhibit London forces. And the thing that we have observed in terms of the trend, the London force increase with increasing mass because the presence of more electrons causes a stronger instantaneous dipole. Okay? Now, let's try to look at the LDF. So it says here, LDF are also larger for more polarizable molecules. So the term that we have here is polarizability. So what does this mean? So let's try to look at the next slides where all materials has C5H12, but they are arranged in a different way. So the question I will ask here, which do you think is the most polarizable? So what can you say about them? All of them has what? C5H12. But look at how they are arranged. So if you're going to take organic chemistry, you're going to write it this way. This one, you're going to write it this way. And this one, you're going to write it this way. You will learn about that on Argo. Don't be too excited. But I'm just showing you by drawing this one, you could see that they have different shape. And that different shape will affect the boiling point. Look what happened. This is 36, this is 28, this is 95. This is 25.8, this is 24.7, this is 22.8. Is there a difference in the molar mass for the three compounds? Yes or no? Is there a difference in the molar mass?
No.
No.
Three compounds?
They're all
The answer
similar.
is no. But how come? Okay, even though there's no difference in the molar mass, there's a difference in their properties. The IMFA usually dictate the properties, the bulk properties of a given compound. So which is the strongest IMFA among the three? Anyone? So I put this as A, I put this as B, I put this as C. So which is the strongest IMFA? Is it A, B, or C? Anyone?
C.
Which is the strongest properties? Is it A, B, or C?
A?
I think it's A.
A.
The answer is A because it has the highest boiling point and it has the highest heat of vaporization. Now, the question now is I'm going to go back. Which is the most polarizable? A, B, or C?
C.
So what's the definition of the polarizable that we have from the previous slide? Okay. London forces are also larger for more polarizable or more easily distorted molecules. So there it is. So which is the most polarizable, A, B, or C?
C.
Which the one can you distort?
C.
That's the reason why I put here the stick structure. So if you're going to look at this, you can still distort this one. This one, there's no way you can distort it. It's already the most distorted thing here. So you cannot distort it anymore. Or the least that you can distort. This is the most polarizable because you can distort it more. You got it? The most polarizable is this one. Look at the structure here. You can still distort it, but this one, no. So the most polarizable one, that's the one that has the strongest IMFA. So the straight chain compound, which is this one, that's the one, okay, that has the strongest IMFA and the highest heat of vaporization, because that's the most flexible and therefore the most polarizable. The most compact compound, it has the weakest and the lowest heat of vaporization. And which is the most compact here? This one. Does that make sense?
Yes.
Yes.
Now, being this as the basis, so we can now say the stronger the IMFA, the higher the heat of vaporization, the lower the vapor pressure, the higher the boiling point, the higher the surface tension, and the more viscous the liquid is, like this one. Okay. So if we're going to look at this polarizability definition, so that means, what does it mean? Flexible. You can still distort it. Okay. If you cannot distort it anymore, that's not that's the least polarizable material that you can have. So if we're going to look at again the things that we have here, so we already observed the trend, right? But the only questions that we have here is why water and glycerol an anomaly. It doesn't follow, okay, the observation that we have higher molecular mass, lower vapor pressure, higher viscosity, and higher surface tension. And it has something to do with their structure. So if you're going to look, this is water, and this is glycerol. So you, in the water, you have an OH here. In the glycerol, you have 3 OH. In the methanol, you have 1 OH. In the sugar, how many OH do you have? Anyone? Anyone who can give me a number?
3.
Is it 3?
Oh,
Anyone?
no.
You always go to the structure of the sugar.
Yes, 6.
So how many do you think OH do you have in the sugar?
6.
Okay. Since oxygen has a lower number than hydrogen, so it will be dictated by the number of oxygen. So most likely, you can have at most 6 OH structure in the sugar. And this OH, okay, so if I'm going to look at this from one of these things. So what's the problem with this one? So OH, why is it OE here? I don't know. What could that be E? I didn't what we call the edit it. It came from the series, okay? In my Gen Chem, in my higher Chem, I asked them to watch an episode of this series and then discuss a chemistry of a scene. Okay. Now, what does this have to do with this OH? So there's another one that we have here called the H bonding. So each molecule has 1 or more OH group. And if you have a molecules with this group, you have an additional force called the hydrogen bonding. How does the hydrogen bonding exist? Your hydrogen serve as a bridge to any of the three electronegative atom, nitrogen, oxygen, and fluorine. So hydrogen bonding is a weak attractive force that exists between hydrogen atoms bonded to a very electronegative atom and a lone pair of electrons on another small electronegative atom. So I can make it like what it has here. So X and Y. And X and Y, okay, can either be N, O, or F. So if you have a hydrogen bonding like water, so you do it like this. So you form some sort of a H bond there. So what happened? If you look at this, hydrogen is the bridge between two oxygen. This is another hydrogen bonding. This is another hydrogen bonding. Okay? Now, what is the result of this hydrogen bonding? That's the reason why you have that anomaly in terms of viscosity, surface tension, and vapor pressure. And this is also why you have this anomaly. What can you say about here? What's the shape that you have here? I don't know if you're going to believe me, but it's just like a Nike logo, right? Like that. So how come water has a higher boiling point compared to the elements in the same column as water? Okay. So if you're going to look at the periodic table, there's an O, and then below the O is what? The S, and then the SE, and then the TE. So if you're going to go down the periodic table, the molar mass increases. So if the molar mass increases, your boiling point should also increase. But how come we have the Just Do It logo here? Because this one has H bonding. So the same thing with this one. If you're going to graph, okay, the compound of a certain element, like for instance, the element where fluorine belongs, or the family where fluorines belong, HF, HCl, HBr, HI, ammonia, PH3, ASH3, and SbH3. So all of them has a higher boiling point compared to the one that has a higher molar mass. And the main reason why they have the Nike logo is this one exhibit H bond. Now, how come CH4 follow the normal trend? What's the main reason? Anyone? Why does the methane follow the same what we call trend? The higher the molecular mass, the higher the boiling point, because methane doesn't exhibit H bonding. Okay? Questions so far before I ask you something with regards to your what we call OWL.
So there are rules to molecules, like the bonding molecules, and if there's H bonding, their molecular mass has nothing to do with the boiling point.
Yeah. Especially if the what we call the molar mass is a little bit close to one another.
Thank you. That makes more sense. So
But-
how do we know when it's an H bond? I'm sorry.
Huh?
How do we know when it's an H bond?
I just mentioned to you that the hydrogen should be in between any of the three most electronegative atoms.
Yes, but then you gave the example that methane is not in, like, it's not one of the H bonds.
Is carbon one of the most electronegative atom?
No.
Then it's not what we call, it's not going to exhibit H bond there's only 3 atoms that can exhibit the H bonding. Okay, hydrogen attached to nitrogen, oxygen, and fluorine. Does it make it clear?
Sorry, yes, now it does.
I'm showing you here the methane because I'm showing you here that if it doesn't have an H bond, it followed the pattern wherein the higher the molar mass, okay, the stronger is the IMFA. Now, there's a full question that I'm going to ask you. What the hell is that? Can LDF beach H bond? So what's the other? Sleeping? So most of you, okay, so for the 9 students, we're still sleeping. So most of you said yes, and that's good because at least you have now quite understanding on how the strength of the IMFA with one another could what we could look like. Okay, so before I answer the question here, let's try to do some sheet work. So let's try to identify all the IMFA that you had expect from the following substance. Oxygen. What does the oxygen has? So how are we going to answer this question? The first thing for you to do is identify the polarity. Because once you have the polarity, you will have an idea which is present. Okay? Is oxygen polar or non-polar?
Non-polar.
Okay?
Polar?
Is oxygen polar or non-polar? So what you're going to do is you're going to write its Lewis structure. And what do you get? Isn't it like this? 1, 2, 3, 4, 5, 6. So 6 atoms or 6 electrons, 2 of them. So that's 12. So this is the one. Is this polar or non-polar?
Non-polar.
Non-polar.
So that's non-polar. So if it's non-polar, what's the LDF that is present? What's the IMFA present? It's only LDF. Make sense? Now, how about the second one? Hydrogen peroxide. Is it polar or non-polar?
Is it polar?
That's how it is, right? So is this polar or non-polar?
Polar.
That's polar. So LDF is present because it's present in everything. What else? Dipole, dipole. Can H bond form here?
Yes.
Yes.
So you have H bond. Now how about this one? CHBr3 is polar or non-polar?
Polar?
Okay, so if we're going to look at this, this is how it looks like. So this one goes there, and everyone goes, I think, to the bromine. So there's a deep, what we call a net dipole moment. So that's a polar. So what do you have? You have LDF. Do you have dipole-dipole?
Yes.
Yes.
Yes. Do you have H bond?
Yes.
No.
No H bond.
We only have LDF and dipole. So can you assign now the IMFA that is present in a given material? Because that's the end game here. If you understand it, you should be able to assign the IMFA in a given material. And then to answer you the question, can LDF beat H bond? I'll bring you to this example. The French fries. What's the raw material for French fries? Everyone familiar with French fries?
Yeah, I've had some before.
Okay, so it's made up of potato. How do you do the French fries?
You need to fry them.
Fry the potato.
You fried it. Okay, so what is the material in frying?
Oil.
Oil.
Oil. So what is
Oil.
oil? Polar or non-polar?
Non-polar.
Oil is non-polar. Another way of knowing if a material is polar or non-polar is if it mixes with water, it's polar. If it don't mix with water, it's non-polar.
Yeah, so non-polar.
Okay. Now, what do you have in potato that will compete with oil? Because once for it to be fried, this thing should be gone. What's that material? Okay. You have your water. Now, the question that we're going to ask, if this is non-polar and this is polar, so this one has H bond, and this one would only have what? What does oil have in terms of IMFA? Anyone?
LDF and dipole.
LDF. Now, this is the question. Which boils first? Is it the oil or the water?
Oil?
How about the others?
Oil.
Which boils first, the oil or the water? Hey, wake
Oil.
up.
Oil.
Oil.
Which boils first, the oil or the water? El aceite or el agua?
Oil.
Isn't it water? Because doesn't like oil have a higher?
This is just one way of me of saying, do you know how to cook? Yes or no?
Wait, I don't understand the question.
Which boils
Oil.
first, the oil and the water? Or we could say, which has the higher or lower boiling point? Because the one with the lower boiling point, that's the one that boils first.
Isn't it water?
So it would be water then.
Yeah, water
Isn't it
water
oil?
boils first.
Okay, let's go back to the basic question.
They boil at the same
First.
time.
I can really see that none of you has done frying real time, or at least
I think water boils first because oil doesn't boil until there's something in it.
Doesn't oil? It doesn't boil, but doesn't it like heat up quicker than water?
Oh yeah.
No, water heats up quicker because oil has a higher.
Boil first?
No,
I'm pretty sure that
Hey,
water
I
boils.
didn't ask for why. The only question that I have is which boils first, oil or water?
Oil, because it gets hot first.
Water. I think it's water. Because oil can get hot, but
It's
it's not going to
water.
start to boil.
Yeah, I think it's water.
Didn't put
Water.
it in the survey.
Change my
I think it's
answer,
water.
Professor.
It's water.
The answer is water. Right? The answer is water
Yes.
first. When you do a frying, right, you put the oil. What happens if you have some water in the things that you fried? When you mix it with water,
The oil, yeah, sure.
right? You hear that sound? Only those who did it knows what I mean. If you have a blank face, that means you didn't do frying in your life. So when you put the oil there, it got hot. Maybe you put what? Your chicken, your fish. But when you add them, why? Because the water, okay, is affecting the oil. And by that time, the water will boil first. And what happened when there's no more water? Your material now will be fried. That's how your French fries is being done. So you remove the water first, okay? And once the water is done, your French fries, which is usually white, will now become yellow. Does that make sense? That your water has a lower boiling point compared to oil. Now, I'm going to tell you the reason why the LDF beat the H bond. What is the molar mass of oil? Oil is what? It's a big molecule. The LDF is an inductive property. It depends on the material. So the bigger the material, the stronger it is. So there will come a time that if you have a very big molecules, it will be much stronger than anything that only has the H bond, the one that has the H bond, even though it's just LDF. Now, what tells me, okay, why water boils first? Okay, because based on my experience in frying, whenever I fried, it's always the oil that is left in the pan after frying. Okay? So this is one way to you to explain that H1 is not always strong. There will come a time that you're going to have a much stronger material that's just made up of LDF, if it's really what we call so big. So the last part that we're going to have in this chapter is the solid. So we talk about some of the properties that we have, okay? Some of the what we call IMFA that we have. So what we're going to do is we're going to apply those IMFA to discuss the different types of solids. So there are 4, and each of their example is being shown here. So this is a molecular solid, a metallic solid, an ionic solid, and a covalent network solid. So how are they different in one another? It has something to do with the structural units and the attractive forces that hold them together. Okay? So let's look at these structural units. A molecular solid, like water, is made up of atoms and molecules, and the one that hold them together are just the IMFA that we have discussed. And the nature of the structural units and the attractive forces, of course, affects the properties that you have in these types of solids. Metallic, on the other hand, these are just made up of the elements that are metals. And what you have there are atoms, that is surrounded by the so-called sea of electrons. So the attractive forces that you have there is metallic bonding. Okay. Yeah, I'm reading your chart. So please don't complain if you're going to have low grades at the during the exam, because it seems to me that you're more active in chat talking nonsense compared to the stuff that we have. Okay. So if we're going to look at this one, the metallic bonding that we have here, this sea of electrons that you have affects the property that you have as a metal. So what's the main property if you are a metal? Anyone? Do you recall from Gen Chem 1? Metals are always what?
Nonpolar.
Good conductor of heat and electricity. And it's something to do with the sea of electrons that it has. Now, ionic compounds, they're made up of ions, and the one that hold them together is ionic bonding. And this includes all the salts. Now, the one that is quite unique is the so-called covalent network. So usually it is made up of atoms. Now, unlike the molecular, the one that hold them together is covalent bonding. And examples that you have here, diamond, graphite, and asbestos. Okay, so if we're going to go to each of them, so if you have a molecular solid, it's made up of atom and molecules, and it's just held by IMFA. The metallic solid, you have metal atoms that could be called the sea of the localized electrons. Ionic compound, usually made up of ions, the cations and the anions, and then held by ionic bonds. So you expect it to be what? They have high melting point and boiling point, because you need higher energy to break the electrostatic bond or the ionic bond that hold them together. Covalent network solid is also like that, because what you have there are covalent bonding. So from this alone, you could say that the molecular solid is a little bit the weakest among all types of solid. Weakest in terms of low boiling point and low melting point, because it's just all IMFA that hold them together. The rest are held by intramolecular forces of attraction. Now, for carbon, they're just made up of what? For the diamonds and graphite. So these are the so-called allotropes. But if you're going to compare the behavior of the two, your diamond is what compared to the graphite? Diamond is the hardest material based on Mohs scale. Your graphite is what? You use it if you have your pencil. The so-called pencil lead, it's not really lead, it's really made up of graphite. So see the properties that you have there. The hardest material compared to one material that is soft. And if you're going to compare the properties that they have, like melting point, hardness, and electrical conductivity, you will see them here. So look at all the molecular. Their value is really low. Why? Because it's just made up of intermolecular forces of attraction that hold them together. Compare it with the metallic, ionic, and covalent network. Look at the values that they have. Because the one that hold them together is some sort what we call an intramolecular forces of attraction. And the nature of their what we call forces that hold them together also affect their properties. Okay, I don't know if you're going to believe with me. Among the thing here, the one that is the hard, the most hard are the metal. Although diamond is listed as what we call the hardest material according to Mohs scale. Okay, so if you're going to look at the melting points, the solids, they have lower. The ionic solids, it depends on the differences in the lattice energy that they have. The melting points of the metals usually vary. One of them is even what? Liquid at room temperature. What metal is that is liquid at room temperature? Anyone?
Mercury.
Mercury. Okay. Now, in terms of hardness, it depends on how easily the structural units can be moved relative to one. I don't know if I'm going to what we call agree with this. Molecular solids tend to be soap. Have you been hit by an ice block, or if you are in a karate event, right? Sometimes they break it with their hands, sometimes with their head. But ice is usually what? Molecular solid. Okay? But it says here, molecular solids tend to be soaps. That's why I'm not sure if I'm going to agree with the statement that we have here. Although network solid like diamond, they're very hard. You usually use it to cut glasses. Ionic compound, they're brittle. Have you tried to hammer salt? And you will see it just easily hammer what we call break into pieces. Metals, on the other hand, malleable. You can easily shape them by hammering them. Okay. Conductivity, metals is the one that will conduct electricity at any form. Ionic solid will only conduct electricity when it is what? Can it conduct in solid form, the ionic solid? The answer is
No.
no. Why? Because the cation ions and anions are not separated. Okay? Materials can conduct electricity if there is the presence of ions. So ionic solids, they can only conduct electricity if you dissolve them in water. Why? Because your what we call the ions that are attached to one another in the solid form, they exist as ions. Okay? They cannot what we call conduct electricity during the solid form. So if we're going to look at here, they also conduct electricity when they are dissolved in water. So if we're going to summarize what we have so far, this is what we have. So melting point, low, variable, high to very high. Okay, and then hardness and brittleness, this is what? Soft to hard. And electrical conductivity, non-conducting for molecular, conducting with metal, and non-conducting for ionic. Covalent, usually they're non-conducting. Okay? Now, what do you need to know on this part of the types of solids? When you're given a solid, you should be able to identify what type it is. So if you're given carbon dioxide, what type of solid is carbon dioxide? Or dry ice? What type of solid is dry ice? Anyone? Dry ice.
Molecular solid.
Okay. Dry ice is molecular. Okay. So if you're asked silver, what type of solid is silver?
Metallic.
Metallic.
It's a metallic solid. How about silver chloride? What type of metal? What type of solid is silver chloride?
Ionic.
It's an ionic solid. So those are the stuff that you need to know here. And I think in my reviewer, I have questions about that. Okay. Now, the last part that you have to know here is the type, or we could say, when do we say we have a crystalline solid and when do we say we have an amorphous solid? Crystalline solid is one wherein there's a well-defined ordered structure in 3D. Amorphous solids, there's what we call disordered structure. And unfortunately, most of our solids are crystalline. Okay? The only solid that is amorphous is glass. But in some book, they even describe glass as not solid. In some book that I read, they describe glass as what? What is the physical state of glass? They describe it as a liquid. Why? Because they said it has the ability to flow. What is their evidence that glass is what they call a viscous liquid? They observed some of these glass pane in cathedrals in Europe, and they found out that they see some movement of some of the colored particles in the glasses there. But the movement can only be observed after 100 years or after long years. Okay, so that's why they called glass in one of the books that I read that it is a viscous liquid. But if you're going to look at the structure of this glass, the way that they said it's amorphous is because it doesn't have a well-defined structure. What others example you can get as a amorphous solid? Anyone? I don't know if you're familiar with this one because you might put another meaning to this. What's a rubber? Where do you use the rubber? Please don't smile. David and Daniel. Tires, right? You know what the tires is? The car tires? Oh my God. What's the process when you do rubber? It's named after a god, vulcanization. So if you're going to look at that material, they don't have an ordered structure. Okay, so that's one of the things that you need to what we call take into consideration about an amorphous solid. Okay, now we go to this so-called crystalline solid. I don't have my daughter to fetch because she's here, so we go to 140. So when you look at this crystalline solid, you have this so-called crystal lattice. So if you're going to look at this, this is the geometric arrangement of lattice point of a crystals. So this is where, remember, I have an example to you with the sulfur, the so-called rhombic and monoclinic. Okay, you don't need to know the 7 crystal system, but I just want to let you know that if you have a crystal lattice, there are 7 arrangements of that. And how are they deeper in terms of the length of their age and the angle that you have. So for you to determine the difference between the two, maybe we put it in terms of the figures. So this is the cubic, 90-degree all angles and the same what we call length of all ages. If one of the length is what we call longer and you still maintain the 90 degrees angle, that's a tetragonal. Okay. Now, if the length, 2 of them are longer compared to that's what we call the orthorhombic. In the monoclinic, I think the Y has a different angle compared to the alpha. The gamma is a different than the alpha and the beta. So these are just a different arrangement of the crystal lattice. I don't need you to learn about this. What do you need to know in this part? Okay, maybe we concentrate with the cubic crystals. So there are 3 possible unit cells: the simple, the body-centered, and the face-centered. So how are they differed? So if you have the simple, you have what? You just have the corners there occupied by an atom or an ion or a molecule. Okay. Now, how is the simple cubic differed with the body-centered? So in the body-centered, you have the whole atom, molecule, or ions inside it. So if you're going to cut it here in 3-dimensional, this is how you're going to look at it. And how is it differed with the face-centered? So how is this different, face-centered different from the body-centered? So here, it's just inside the cube. But here, what happened? in addition to the one that is inside the cube. Oh no, this is not inside the cube. This is in the what? 6 sides. So you have there, you have there, you have here. So 1, 2, 3, 4, 5, 6. So the best way to imagine here is you have an the dice. So simple cubic, it's all dice. Okay. Body centered, there's an atom inside the dice. And then face centered, all the sides, they have an atom there. And if you're going to slice it here, so only 1/2. Now, what do you need to remember here? So we have this term called coordination number. Okay. So when you're talking about the coordination number, this is just a number that is assigned to tell you how compact the given solid is. And there is usually an associated number if you are a simple body-centered or face-centered cubic. Okay, so when you say coordination number, this is defined as the number of atoms or ions surrounding atom or ions in a crystal, and it's a value of a measure of how tight, okay, the spheres are packed together. So a simple cubic, it's 6, body-centered is 8, face-centered is 12. And in addition to that, you should be able to tell how many atoms do you have per unit cell. So in a simple cubic, they said you have 1. Why? You have how many here? 1, 2, 3, 4, 5, 6, 7, and then there's 1 there, 8. But in each of these, what we call crystal lattice, there's only 1/8 of that. So 1/8 times 8 will give you 1. How about in the body centered? How many atoms do you have per cell? So the 8 that you have on this side times 1/8 and 1 atoms in the center. And here, what do you think the magic number here? 4. So where do we get the 4? Again, we have the 8 there times 1/8, and how many sides do we have? 6 sides, and each side will get 1/2. So that means 6 times 1/2, that's 3 plus 1, you have what we call 4. So this is the thing that may come out in your exam. Okay, what's the coordination number and how many atoms that you have there in a given unit cell. Okay, so that's all in chapter 11. And we have time to get some question. So during the time that I stay longer here, we can utilize it for you to ask question. So question. So you're now ready to answer the assignment that you have. And I would like to remind you, do you have your owl already? Because I think some of you, I cannot still see your name in the owl.
I actually have a question about the discussion board.
Okay. So you just did something there about the question being asked.
No, it's because on my computer, it says that it's due today at 5 p.m. But some of my other classmates, it says that it was due at like a different time. So I just wasn't sure what time it was due.
I'm not sure also what time it's due. So usually whatever it says there.
Okay.
Because if I'm not mistaken, I think it should be due last week, if I'm not mistaken. I don't know. You're not the first one, because I have a student in my other class yesterday. He told me that the Zoom link that he got is that one that I have posted earlier, but I removed it. But unfortunately, he's the only student who got it wrong. The other students were able to show up in class, except him. So I don't know what's the thing with the classes. But all I know with the discussion board, I think, if I'm not mistaken, I did it twice because I cannot show it up to you. And then all of a sudden I was able to do that thing. So maybe some, I don't know, but I erased already the old one, if ever, in case. That's why the thing that I want is whatever you are asked to do, please do it as soon as possible. Okay. But if I'm not mistaken, you should, I'm going to take a look at it. Okay. And see how many had done that. But the thing is, I'm going to be strict with the assignment. Okay. So the due of that is 12 noon before our class. And then maybe by 12:05, I'm going to answer the questions to that. So if you're not being able to, what we call log in by 12:05, then in the recording, that's the first thing that will come out. Okay. And that's the only time I'm going to go over that thing. I may not be able to post the answer, but what I'm going to do is I'm going to discuss the answer on that thing. So by now, you should be able to answer the questions that you have there. Although I think some of you has already uploaded it.
I have a quick question about the OWL.
Mm.
I signed up for the class. It says the next assignment due is Chapter 11 Mastery, but isn't Chapter 11 Chem
The
1?
Chapter 11 should be due by 9, a week after we're done with Chapter 11. So we're done with Chapter 11 now. So it will be due by February 9.
I was getting confused with the labs and the chapters. I figured that Chapter 11 was Chem 1. But
No, Chapter 11, I think, is until in your, what we call in the OWL. That's where you start.
Yeah, it's due on the 9th. Yeah. I just wanted to make sure that was right, though.
If I'm not mistaken, I have not looked at it, but I know I put it at February 9, but I don't know what time.
6 p.m.
That's all I can remember. When I touch the OWL B2, which I can open now.
Yeah, it's 6 p.m. on the 9th.
I'm not sure if I make it at 5 or 6.
It's 6.
And I also email you, if I'm not mistaken, the Learning Center. The information that they have. There are 3 tutors there for chemistry. The mastery, right? So I put 6 p.m. February 9 as the deadline for Chapter 11. So question on that?
Sure.
So in terms of the users, these are the one that is using the OWL so far, the one that is enrolled. So the name of the game here is you're not going to be left behind. Because once you're left behind, it's going to be hard for you. Okay? And you know that from your experience in Gen Chem 1. So if you're still doing the same thing as your Gen Chem 1, I think you should change, because this Gen Chem 2 is a little bit more challenging than Gen Chem 1. And I hope you getting used to the system that I had before, don't be like that. Okay? Because if you're going to put the same thing as you did in Gen Chem 1, most likely your grades will be a little bit lower. So this is the one for those who are my students before. Okay, so this is not as easy as Gen Chem 1. But I have some students before who perform better in Gen Chem 2 than Gen Chem 1. And then when I asked him, oh, because I'm just really trying to have a good time in Gen Chem 1. And when I got the grade that you gave me, it woke me up. So I told myself I'll be better in Gen Chem 2. So that's the main reason that they have. Okay. So as I've told you, you just have to do it the chemistry way, or else the letters in the chemistry will take care of you at the end of the semester. So question. So we're done with chapter 11. So we start with chapter 12. Okay, they said all chemists have solutions. So we're going to go with solutions. So they said if you're not part of the solution, then you're part of the problem. So question. So if none, see you on Thursday. Please upload your assignment, okay? So the assignment, it will be uploaded there. I think there's a depository there where you can upload the assignment one. Upload it in PDF form. If you're going to upload it at HEIC, I cannot open it, okay? So please don't upload it in the .HEIC form. So enjoy your snow day.
Thank you, Professor.
Thank you.
Thursday.
Thank you. This is gonna be every time
I see
now.
the smile again.
Hey, buddy.
Thank